It is often said that human beings landed on the moon in 1969, that Neil Armstrong took that historic first step, leaving the first footprints on the lunar surface. Yet, when we examine the physics, the technology, and the sheer audacity of such an endeavor, the question arises, how was it even possible? To understand this, we must step back not just to the 1960s, but to the very nature of space, of gravity, and of the limits imposed by our universe. The moon, our nearest celestial neighbor, sits at an average distance of approximately 384,000 km from Earth, a vast expanse in which no human had ever ventured before. Crossing this gulf was not merely a feat of engineering, but a confrontation with the raw, unforgiving forces of physics. Any object leaving the surface of Earth must contend with gravity, a force that pulls with relentless certainty. To escape this pull, a rocket must reach what we call escape velocity, approximately 11.2 km per c. That is over 40,000 km per a speed, at which any small miscalculation could prove catastrophic. And yet in the late 1960s, humans engineered machines capable of doing precisely this, directing them with a precision that is almost unimaginable considering the computational power available at the time. We tend to underestimate just how difficult it is to navigate in space. Unlike a car on a road or a plane in the air, a spacecraft has no friction, no resistance to slow it down. Every maneuver must be calculated with exquisite care. A misalignment of even a fraction of a degree in trajectory could send a spacecraft hurtling past the moon or back into the void of space. The Apollo program, which accomplished this monumental journey, relied on guidance computers with less processing power than a modern calculator. Yet, these primitive devices had to perform real-time calculations, continuously adjusting for the gravitational influences of both the Earth and the Moon. One might wonder how it was even conceivable that such technology operating under such constraints could achieve a perfect rendezvous between the lunar module and the orbiting command module. It is a testament not only to human ingenuity, but also to the incredible precision dictated by the laws of physics. The journey itself was fraught with hazards. Cosmic radiation streams constantly from the Sunday carrying enough energy to damage both living tissue and electronic circuits. The Van Allen belts, regions of trapped charged particles surrounding Earth, present yet another invisible gauntlet. The Apollo spacecraft had to traverse these belts in such a way that minimized exposure, a maneuver that required a precise understanding of space physics that had never been applied on this scale before. In addition, the vacuum of space is merciless. Without atmospheric pressure, any leak in the spacecraft or failure of the life support system would be instantly fatal. Oxygen levels had to be maintained within strict tolerances. Temperatures had to be controlled across extremes ranging from -150°C to +120°C, and micrometeoroids traveling at tens of km/s could puncture a spacecraft in an instant. The very environment of space is hostile beyond human comprehension, yet humans traversed it to reach the moon and return safely. Landing on the moon presented an entirely new set of challenges. The lunar surface is covered in a fine dust, jagged and abrasive, with rocks that are jagged and uneven and craters that can extend for hundreds of meters. The lunar module had to descend from lunar orbit, reduce its speed from thousands of km/h, and execute a soft landing with a precision of mere meters. All while the astronauts relied on visual cues and guidance systems that were remarkably primitive by today's standards. Imagine descending onto a world where the only light comes from the Sunday, casting stark shadows that obscure depth perception. With no air to slow your fall, every action had to be exact. Every error could have been fatal. And yet, with remarkable skill, the astronauts touched down, achieving what many at the time considered impossible. Yet the challenges did not end with landing. The moon's gravity is only 1/6 that of Earth, which, while helpful for lifting off again, presents unusual effects on human movement and machinery. Simple tasks such as walking or handling tools became complex due to the altered physics of motion. Experiments designed to measure seismic activity, the moon's composition, and the behavior of solar wind particles had to function in this alien environment, transmitting data back to Earth across hundreds of thousands of kilometers without error. Communication had to contend with time delays, signal degradation, and the challenges of coordinating multiple systems with perfect timing. Every step, every experiment, every return maneuver relied on an intricate choreography of physics and engineering. The return journey posed its own set of seemingly insurmountable difficulties. The lunar module, now partially expended and with limited fuel, had to ascend from the moon's surface, rendezvous with the orbiting command module, and execute a trans-Earth injection burn. Each burn of the rocket's engine, each adjustment in trajectory required precision down to fractions of a percent, because any miscalculation could send the spacecraft on a collision course with the moon or into deep space. Even a minor deviation could prevent re-entry into Earth's atmosphere, where the spacecraft would face temperatures exceeding 3,000 degrees C as it pierced through the atmosphere at tens of thousands of km per h-hour. Yet, with meticulous planning, careful execution, and an understanding of orbital mechanics that was revolutionary for its time, these seemingly impossible feats were accomplished, returning humans safely to Earth. When we reflect on these achievements, it becomes clear that the Apollo moon landings were not merely a triumph of human willpower, but a triumph over the very laws of physics that seem to conspire against such ventures. The precision required, the understanding of orbital mechanics, the control over propulsion, navigation, and life support. All of these represent an extraordinary mastery over a universe that does not yield easily. Yet, as extraordinary as it was, the moon landing is just the beginning of what physics allows. What human ingenuity can achieve when we engage with the universe on its own terms. If we extend our gaze beyond the moon, to Mars, to the asteroids, and beyond, the challenges only multiply. Mars lies hundreds of millions of kilometers away, and a journey there requires a spacecraft to operate autonomously for months with life support systems sustaining humans in an environment far harsher than the moon. Radiation exposure becomes a lethal concern. Propulsion systems must be far more efficient, and the landing on Mars, unlike the moon, is complicated by a thin, unstable atmosphere that prevents simple parachute-assisted descents. Yet the lessons learned from the moon provide a foundation, a blueprint for extending humanity's reach into the solar system and eventually the stars. The moon demonstrated that when we understand the forces that govern our universe, when we apply the laws of physics with precision and creativity, the impossible becomes merely difficult. Even now, we are still unlocking the secrets of space. Advanced telescopes reveal that planets orbiting distant stars are abundant, suggesting that the conditions for life may exist elsewhere. We are developing nuclear propulsion systems, ion drives, and even theoretical warp drives that could allow us to traverse the solar system in weeks rather than years. Artificial intelligence is beginning to assist in navigation, in predictive modeling, and in the management of life support system. Yet, all of these technologies are extensions of the same principles that made the moon landing possible: an intimate understanding of physics, engineering, and the courage to operate at the limits of human capability. In considering the moon landing, we must also confront the nature of reality itself. The moon is not just a distant rock orbiting Earth. It is a laboratory in which the interplay of gravity, motion, and material composition becomes tangible. It is a proving ground for human adaptation, both physiological and psychological. The success of the Apollo missions forces us to confront the possibilities inherent in our species. If we can navigate the perilous void between Earth and the moon, If we can execute maneuvers that defy intuition and rely entirely on the precise mathematics of motion, what other frontiers might we conquer? The moon landing stands not as a relic of the past, but as a challenge to the present, an invitation to expand the boundaries of what we consider achievable. Ultimately, the moon landing forces us to ask a profound question. What does it mean for something to be impossible? Physics, after all, is unforgiving. It is a set of universal rules that do not bend to human desire. Yet, within these rules, there is a vast landscape of possibility, a domain in which skill, knowledge, and ingenuity allow us to achieve what seems beyond reach. The Apollo missions remind us that the impossible is often merely the improbable, constrained by our understanding and limited by our technology, but never beyond the realm of discovery. In this sense, the moon landing is not a historical curiosity. It is a testament to the human capacity to engage with the universe, to understand its laws, and to use that understanding to venture beyond our terrestrial confines. As we look toward the future, the moon stands as the first chapter in an ongoing story of exploration, of discovery, and of the relentless pursuit of knowledge. The challenges were immense, the obstacles daunting. Yet, they were surmounted through a rigorous application of science and mathematics. Every calculation, every maneuver, every successful return from the moon reinforces a central truth. The universe, for all its complexity, is a place where intelligence, courage, and precise reasoning can achieve what was once deemed impossible. And perhaps this is the most important lesson of all, that the limits of human achievement are defined not by the impossibility of the universe, but by the reach of our curiosity, our ingenuity, and our willingness to confront the unknown with reason and with courage. Yet to truly appreciate the moon landing, we must examine the technological framework that made it possible. Rockets are the primary vehicle of space exploration, but their design is constrained by fundamental physics. The chemical energy contained within rocket propellants must provide enough thrust to overcome Earth's gravity while also carrying fuel for every subsequent maneuver. This leads to an exponential challenge. Every kilogram of payload requires exponentially more fuel to lift it into space. The Saturn V rocket, which propelled humans to the moon, represented the apex of this engineering challenge. Standing over 110 meters tall, it was not merely a machine, but a mechanical embodiment of human understanding of combustion, thermodynamics, and material science. Each stage of the rocket had to ignite at precisely the right moment, separate cleanly, and continue the journey without error. Any deviation, no matter how small, could have resulted in catastrophe. The successful design of the Saturn V required not just intuition, but rigorous calculation, experimentation, and a profound understanding of the physics that govern rocket propulsion. Consider the navigation challenges alone. Unlike terrestrial navigation, which relies on landmarks, roads, or GPS satellites, space navigation requires calculation of orbital mechanics across vast distances. Astronauts had to move along trajectories defined by Newton's laws of motion and gravitation. The moon does not remain fixed in the sky. It orbits Earth, which itself orbits the Sunday. The Apollo mission required a perfect understanding of these celestial dynamics. Each burn of the spacecraft's engines had to be calculated in advance, adjusting for velocity, position, and gravitational influence. The slightest misalignment could result in missing the moon entirely. In many ways, the mission was less a test of human strength and more a testament to the precision of mathematics applied to the physical universe. The lunar module itself, the small craft designed to land on the moon, was an engineering marvel. It had to function in a vacuum, operate at extreme temperatures, and allow humans to survive in an environment devoid of air or pressure. Its engine was designed to throttle up and down, a capability not common in rocket engines of the era, to provide controlled descent. Landing on the moon is not simply a matter of touching down. It is a precise interplay of physics, requiring constant adjustment to the module's velocity, trajectory, and orientation. Astronauts had to monitor instrumentation, adjust for unexpected terrain, and respond to sudden anomalies, all while the moon's reduced gravity altered the mechanics of movement in subtle but profound ways. The very act of landing on the moon required a human-machine partnership with unparalleled precision. Yet even more remarkable is how the moon landing challenged our understanding of human physiology. In a microgravity environment, blood flow, muscle function, and vestibular balance are all altered. Astronauts must endure these changes while performing complex tasks, carrying equipment, and maintaining cognitive function. Radiation exposure, particularly from cosmic rays and solar flares, poses long-term risks to both the body and the brain. Life support systems had to precisely regulate oxygen, pressure, humidity, and temperature, maintaining an environment in which humans could survive not just for hours but for days, sometimes weeks. The moon then is not simply a physical challenge. It is a test of our ability to engineer life itself in conditions utterly alien to Earth. Perhaps most astounding is how all of these variables, propulsion, navigation, life support, radiation, and human physiology, were managed with computational resources that are laughably small by modern standards. The Apollo guidance computer had a fraction of the processing power of a contemporary digital watch. Yet, it performed real time calculations, adjusted trajectories, and interfaced seamlessly with human decision. This illustrates a profound principle. Mastery of physics and mathematics can compensate for limitations in technology. When one understands the underlying laws of the universe, one can design systems that function reliably even under extreme constraints. But let us go further to the broader implications of this achievement. The moon landing was not merely a historical milestone. It was a doorway into understanding our place in the cosmos. By leaving Earth and setting foot on another celestial body, humans began to transform themselves from creatures of a single planet into citizens of the solar system. This shift in perspective is subtle but profound. We began to realize that Earth itself is a small, fragile world suspended in the vastness of space. The moon landing provided a glimpse into the universe as it truly is, a realm governed by unyielding laws, yet accessible to intelligent life capable of comprehending and exploiting these laws. This perspective also raises deep questions about our future. If humans could overcome the immense difficulties of reaching the moon, what does that suggest about the potential to explore Mars, the asteroids, and the outer planets? Mars, with its thin atmosphere, extreme cold, and dust storms, presents challenges far greater than those of the moon. A mission to Mars requires months of travel, autonomous life support, and protection from radiation levels far higher than those encountered near Earth. Yet, the principles remain consistent. An understanding of physics, mastery of engineering, and rigorous application of mathematics make such ventures feasible. The moon landing, in this sense, serves as a template, a demonstration that the laws of the universe, while formidable, are not insurmountable. Even more provocatively, the moon landing invites us to contemplate the ultimate boundaries of possibility. If we can land humans on the moon, could we manipulate gravity itself? Could we one day travel to exoplanets orbiting distant stars? The physics required for interstellar travel is extreme, involving concepts such as warp drives, generation ships, or the harnessing of antimatter as propulsion. Yet, these concepts, though speculative, are grounded in the same principles that allowed Apollo astronauts to land on the moon. Each advancement in technology is simply an extension of our understanding of the universe, a bridge from the known to the unknown. Furthermore, the moon landing challenges our conception of risk and probability. It is easy to underestimate the extraordinary odds that were overcome. The probability of mission failure, whether due to mechanical malfunction, miscalculation, or human error, was substantial. Yet through redundancy, planning, and scientific rigor, every obstacle was mitigated. This illustrates a central truth about scientific progress, that mastery over complex systems does not rely on luck, but on a thorough understanding of the underlying principles, coupled with disciplined execution. The moon also represents an ongoing laboratory for physics and astronomy. Lunar geology provides insights into the early history of the solar system, revealing clues about planetary formation, asteroid impacts, and the evolution of celestial bodies. The moon's relatively static surface preserves a record of cosmic events that Earth's dynamic environment has long erased. By studying the moon, we gain knowledge not just about a neighboring celestial body, but about the formation of planets, the behavior of orbital mechanics, and the forces that have shaped our solar system over billions of years. In this way, the moon landing is not a closed chapter of history, but a living gateway into cosmic discovery. As we examine the moon landing through the lens of physics, engineering, and human endurance, it becomes clear that it was in every sense a confrontation with the impossible. Yet, as with all great scientific achievements, the impossible becomes a frontier for exploration, a challenge to understanding, and an invitation to expand the limits of human capability. The Apollo missions remind us that the universe is not a fixed arena, but a domain of possibility constrained by laws that, when understood, can be navigated with precision and creativity. The moon landing is not merely a historical achievement. It is a paradigm for how humans can interact with the cosmos using intellect, ingenuity, and perseverance to achieve what at first glance seems beyond reach. And perhaps the most profound implication of all is philosophical. If humans could overcome the enormous challenges of reaching the moon, what else is possible? Could we one day terraform planets, harness the energy of stars, or even travel between galaxies? These questions are not purely speculative. They are grounded in physics, in mathematics, and in the human capacity to understand and manipulate the universe. The moon landing in this sense is a testament not only to our technical ability, but to our potential as a species capable of transcending the limits of our immediate environment, stepping into a broader cosmic narrative that stretches beyond Earth itself. In conclusion, when we examine the moon landing through the lens of physics and reason, we are confronted with a paradox. What seemed impossible given the harsh realities of space, the limitations of technology, and the fragility of human life was made possible through a rigorous application of knowledge and creativity. It is a reminder that the laws of the universe are not arbitrary obstacles, but guiding principles that, when understood, allow us to expand the horizons of possibility. The moon landing stands as both a historical achievement and a symbol of potential, a demonstration that even the most improbable ventures can be realized when intelligence, courage, and scientific understanding converge. And as we continue to look toward the stars, the legacy of Apollo serves as both inspiration and instruction, showing us that the universe, vast and indifferent, is nonetheless navigable, if only we have the wisdom and courage to understand it. Beyond the immediate technical challenges of the Apollo missions lies a subtler yet equally profound domain, the frontier of knowledge that the moon opened for humanity. Lunar exploration demonstrated the interplay between physics and human ingenuity, revealing that our understanding of orbital mechanics, propulsion, and material science is not merely theoretical but directly applicable to survival in the harshest environments. For instance, consider the trajectory calculations required for the lunar module to descend from orbit. These calculations were not static. The spacecraft had to respond in real time to minor gravitational anomalies, to the uneven distribution of mass within the moon, to the subtle tugs of Earth's gravity. The moon is not a perfect sphere. Its mass concentrations or masscans create local variations in gravity which can alter the orbit of a spacecraft by several meters over hours. The Apollo engineers had to incorporate these irregularities into the mission planning, demonstrating an extraordinary integration of astrophysics, applied mathematics, and engineering. Furthermore, the moon landing forced humanity to confront the physical limits of our bodies in alien environments. Microgravity affects cardiovascular function, bone density, and muscular structure. Extended exposure leads to atrophy, disorientation, and even changes in cellular processes. The Apollo astronauts, although on relatively short missions, experienced these effects, prompting researchers to develop countermeasures such as specialized exercise protocols, suit designs, and nutritional regimens. These solutions, initially devised for lunar exploration, now form the foundation for long-duration spaceflight studies, preparing us for missions to Mars and beyond. In this sense, the moon was both a destination and a laboratory, teaching us not only how to navigate space, but how to preserve human life within it. The lunar environment also posed extreme thermal and radiation challenges. Without an atmosphere, the surface experiences temperature swings of more than 270 degrees C between lunar day and night. Solar radiation, particularly during periods of heightened solar activity, can be lethal. While cosmic rays bombard the moon continuously, carrying energy sufficient to disrupt both electronics and biological tissue, the Apollo spacecraft had to shield its occupants from these hazards while maintaining operational efficiency. This required precise material science and innovative engineering. Every panel, every circuit, every system had to function flawlessly under conditions that were completely alien to Earth. It is a demonstration that mastery over physics is not abstract. It is life-preserving. Yet, the moon landing also raises questions that extend beyond engineering into fundamental physics. By studying lunar geology, scientists discovered that the moon's surface preserves the record of impacts and radiation over billions of years. Unlike Earth, where geological activity constantly recycles the crust, the moon's static environment provides a window into the early solar system. From the distribution of craters to the chemical composition of lunar soil, we can reconstruct events that occurred long before humans existed. This knowledge informs our understanding of planetary formation, the origins of water on Earth, and the history of asteroid impacts. In other words, the moon is not simply a destination. It is a key to understanding the history of our own planet and the broader cosmos. From a theoretical perspective, the moon landing exemplifies humanity's growing command over the laws of physics. Each maneuver, each system, each calculation was a direct application of principles first formulated in classical mechanics, thermodynamics, and electromagnetism. Newton's laws, so elegantly simple on paper, became the guiding equations for life or death decisions hundreds of thousands of kilometers from Earth. Maxwell's equations dictated the behavior of communication systems across space. Einstein's relativity, though only subtly affecting mission planning, ensured that timing and synchronization could be accurately maintained, accounting for small but measurable differences between spacecraft clocks and those on Earth. The moon landing then was not a triumph of improvisation, it was a triumph of science itself. As we contemplate the future, the implications become even more remarkable. Lunar exploration was the first step in a broader human project. The colonization of the solar system. Establishing permanent bases on the moon will require sustainable life support, efficient energy production, and protection from radiation. Advanced propulsion systems such as nuclear thermal rockets or ion drives could reduce transit times to Mars and beyond, while autonomous robotics can prepare infrastructure before humans arrive. Artificial intelligence will assist in navigation, environmental monitoring, and resource management, making human settlement more feasible than ever before. Every principle proven during the Apollo missions is now a stepping stone toward the next era of space exploration. In a broader context, the moon landing also challenges our philosophical assumptions about possibility and limits. Physics imposes strict constraints, yet within those constraints lies a vast landscape of achievable outcomes. The impossible is often simply a function of our knowledge or lack thereof. By applying rigorous reasoning, empirical observation, and precise experimentation, humanity was able to bridge a gap that once seemed insurmountable. This suggests a profound principle. The boundaries of human achievement are defined not by the universe itself, but by the limits of our understanding. The moon landing exemplifies this principle in concrete, undeniable terms. Moreover, the moon provides a laboratory for future technological innovations. In situ resource utilization, or the ability to use lunar materials for construction, life support, and fuel production, is now a critical area of research. By extracting oxygen from lunar regolith or hydrogen from ice deposits at the poles, we can reduce dependence on supplies from Earth, paving the way for sustained human presence. Solar energy unobstructed by atmosphere or weather could power advanced systems and support scientific research. Every innovation on the moon will inform our understanding of how humans might survive on Mars, the moons of Jupiter and Saturn, and even beyond the solar system. From a cosmological perspective, the moon landing serves as a reminder of the human capacity to engage with the universe at its most fundamental levels. The moon itself is a witness to the formation of planets, to asteroid bombardments, and to the evolutionary history of our solar system. By venturing there, humans have begun to read the universe as a text, interpreting its history and predicting its future. Each mission, each experiment adds to a growing body of knowledge that may one day allow us to manipulate environments, harness energy on planetary scales, and extend life beyond Earth. The moon landing is thus both an historical achievement and a template for future exploration, demonstrating that with knowledge and precision, humanity can engage with the cosmos directly. Consider also the implications for interstellar travel. The principles proven in lunar navigation, precision timing, trajectory calculation, propulsion efficiency, life support, and radiation protection form the foundational knowledge for journeys beyond our solar system. A mission to the nearest star Proxima Centauri would require propulsion systems orders of magnitude more powerful than chemical rockets, perhaps utilizing nuclear fusion or antimatter. Life support systems would need to sustain humans for decades or centuries, potentially relying on cryogenic stasis or multi-generational habitats. Even the challenges of radiation, microgravity, and psychological health first confronted on the moon must be resolved. The Apollo missions, then, are the opening chapter in the story of humanity as a space-faring civilization, demonstrating that when we apply science rigorously, the universe itself becomes a navigable domain. Finally, the moon landing invites us to contemplate the broader destiny of humanity. If we can traverse the gulf to the moon, understand and manipulate the laws of physics to survive there and return safely, then the universe is not a barrier, but a frontier. The moon is a stepping stone, not an endpoint. From these first footsteps on a distant world, we can project forward to permanent lunar bases, Martian colonies, asteroid mining, and eventually interstellar exploration. The human journey into space is a continuous trajectory defined by the rigorous application of knowledge and the willingness to confront danger with intellect rather than fear. In the end, what once seemed impossible, landing humans on the moon, is a reminder of what can be achieved when the mind fully engages with the universe. It teaches us that the constraints imposed by physics are not limitations in themselves, but guides that, when understood, allow us to navigate the cosmos. Every calculation, every engineering decision, every carefully measured burn of the spacecraft engines reflects the power of reason, applied to nature. The moon landing is not just a historical event, it is a paradigm, a proof that intelligence, courage, and meticulous application of scientific principles can overcome even the most formidable challenges. As we continue to explore, the lessons of the moon will guide us. We will develop new propulsion systems, advanced AI, autonomous robotics, and sustainable life support. We will learn to manipulate environments on planetary scales. We will study the cosmos, not just from afar, but with the direct participation of human beings. The moon landing, seemingly impossible at the time, demonstrates that no frontier is beyond reach when we combine intellect, creativity, and the rigorous application of science. And perhaps most importantly, it reminds us that the universe, vast and indifferent, is nonetheless comprehensible, navigable, and full of opportunities for those who dare to understand its laws and harness its possibilities. The Apollo missions, therefore, are more than historical milestones. They are symbols of human potential, proof that the impossible can become possible when we engage with reality, not through wishful thinking, but through precise understanding and disciplined action. They challenge us to envision the next steps: Mars, the moons of Jupiter and Saturn, interstellar travel, and the eventual settlement of humanity across the stars. Each challenge will be immense, each calculation exacting, and each hazard profound. Yet the mover landing assures us that with knowledge, courage, and persistence, there is no limit to what we may achieve. The impossible, it seems, is merely a frontier awaiting human reason to